or whether it's not a data science, or you will simply get some software problem statement or day-to-day life problem statement. So the first thing is interaction between the two people who actually starts with a statement. For example, in my case, or in our case mostly, it is the interaction between the industry and interaction between the people who are actually going to develop a solution for that problem statement. So the first requirement, if you see here, I mean, if you people are able to see my mouse pointer, so you can see the first is the define business requirement. So what I mean to define business requirement is, so for example, let's suppose that we have some company who are actually manufacturing the gas turbines actually for the power generation, and they may come you, hey, we have a problem in our gas turbines, they are getting heat up after 500 or 600 working hours. So can you actually tell me what's the reason behind that, why it's getting heat up on the basis? So obviously, because we as a data scientist, we don't go into the physics of a turbine, but we directly tell them, okay, we can solve it, but do you have any data to provide us? So this is the initial business interaction between the data scientists, or between the business analysts, and between the industrial owners who are actually giving us the problem statement. So this is when we start this interaction. In this, we uncover almost about everything. For example, hey, okay, you are giving me a data science problem statement for turbine. Can you please tell me how you are actually collecting data from turbine? Where are those actually different sensors fitted on turbine? Are you with me, everyone? So actually, I'm just trying to make it, I mean, so much simple so that you can understand why. Because when we have an interaction with the business about this problem statement, it's never we directly go and start visualizing data and come with some insights. But we, before visualizing, we have to get a better understanding actually how turbine is working. Okay, turbine has a blades, turbine has a compressor, turbine has then a fuel ignition. How actually this all thing is working, then only I can come to some place where I can guess, hey, actually this temperature rise is because of X, Y, or Z things. So this is all interaction which happens before any visualization, any data collection. So before anything, we actually ask them so many questions. Okay, what are the different locations where this turbine is? Oh, someone is. Can please? I'm hearing a lot of background noise. Someone. Okay. So who is this actually? Someone.
Yeah, Manish sir.
Sir, can you just start the slideshow?
Yeah,
It will be.
Farooq, but you do one thing. You
Okay.
you once again you unshare your screen first.
Okay. Okay.
Then
It's not.
then go first for the slideshow.
Okay.
And
Okay.
then share the screen.
Oh, so they are not able to see screen.
They are not. No, they want the slideshow.
Okay.
What you do, you unshare first.
Okay. Okay.
Yeah.
Okay.
Now go for the slideshow.
No, okay. I actually intentionally kept it like this.
Okay, okay.
Okay. Okay. So.
And then go for the shared screen.
Okay, we can do in other way also. I mean, first doing this screen share and then go for a slide.
There is very hot over there. You are wearing.
Yeah, it's pretty hard. I mean, it's.
Oh, I don't think in Bangalore it's too hot.
No, this year it's hot everywhere. So now you people are good. I mean, you are
fine.
Okay.
It's fine. It's fine now.
Okay, so the second step, I mean, after that, I mean, when we have an initial questionnaire with the business owner or with the people who are actually coming with a problem statement, so we go for a data collection. So this data collection and data cleaning and data exploration and analysis. So these three phases are of data acquisition. I mean, most of people will question, hey, data exploration and data analysis is actually the thing where we are coming up with some analysis. So how it is in a data data acquisition part. But these three are very interactive sessions. I mean, we never reach to the data modeling phase unless we will not have a complete clearance on these three things. So these are back and forth steps. Like for example, I do a data collection. I mean, I'll actually give, brief about everything of these, but give me some time. Before that, I'm explaining how it's actually working. So when we have a data collection here, actually, and so as I already told you that, sorry, data collection and data cleaning and data exploration, these three phases actually come in a data acquisition. And most of our time, nearly if we say 80% of time is being given in this part. I mean, then after these, we go for a data modeling. So data modeling is the phase where we actually decide, hey, what our problem statement is. For example, if it is in a do we have a do prescriptive analytics, do we have to do a diagnostic analysis, or do we have to actually do predictive analytics? So for example, prescriptive analysis, I mean, in simpler terms, for example, you went I mean, anyone went to the doctor, and we tell him, hey, we have these things, we are, I mean, suffering with these things. For example, I'm having a temperature, so I was not able to sleep in a night, and also I felt, I mean, sleepless nights, and all those steps. When all those things we tell to the doctor, so and doctor ultimately comes and writes some medicines. Okay, you can take these medicines, you will feel fine. So this type where you actually analyze the person or analyze any data set and ultimately come on a decision and give in inference, you give some measures. Hey, you can take these measures so that you will not have this problem again. This type of analysis is called prescriptive, where you are actually prescripting something. For example, okay, your turbine is getting hot when it's running 600 working hours continuously. Can you do one thing? Can you actually stop every time it after 100 hours for a 5 minutes, for a 10 minutes? So this is prescription, where we are not predicting what will happen, where we are not diagnosing, but we are prescripting him. We are actually forcing him to take some steps to stop this. So now another thing is diagnostic. So diagnostic is actually where you diagnose. Just to go, for example, we are seeing that okay, in a class of 100 students, we have 50 girls and 50 boys, but we always saw that the 50 girls are outperforming boys in everything. So we got curious. Okay, they are performing, I mean, very good, but what is the reason? Then we go in a data set. We collected their work, what they are doing at a home, how many hours they are spending, what are their curriculum activities other than the studies, what are their friend circle. Let's suppose these features we take as a variables, where we are actually ultimately analyzing their performance in a class. And in this whole scenario, when we consider all those variables and we come up with, okay, these were the reasons. Actually, these were the reasons. I mean, what actually caused these things? I mean, for girls outperforming boys. So this is called diagnostic. So we don't actually now prescribe to them anything. We don't say it right now. For example, boys, hey, you have to stop. Actually, you are more in a curriculum activities than your studies. I mean, you are not having enough hours of study at your home. So this type of thing is called a diagnostic, where you just diagnose, where you just stop. For example, someone went to a doctor and doctor just diagnose, okay, it's a kidney failure actually. So this is called a diagnosis. Now another thing is called as a predictive analysis. So predictive analysis is a type of analysis where we predict what is going to happen in a future. So I mean, most of the people see two type of analysis, like a predictive analysis and forecasting. Though they are similar, but they are not the same. So forecasting is different than a predictive analysis. Forecasting is mostly happening on a time dependencies. For example, okay, my market sales in 2019 was X, and my market sales in 2018 was Z. So I want to predict what will be my market sales in 2020. So this is a time dependent. If we take it only as a time dependent entity, at this time it comes as a forecasting. So I'm forecasting, for example, weather. I am forecasting weather. I'm not predicting weather. I'm forecasting. I'm saying what is going to happen in future. So that's a forecasting. But predictive is where we predict, where we actually are going to say what is going to in future, not only with the time constraints, but also with other variable dependencies. For example, as I was giving example of a turbine. So I'm going to tell him, okay, if you don't stop after every 1 hour and your turbine is actually heating to the extent where there is a delta temperature difference between the upper casing and the lower casing, this thing is going to cause you a wear and tear in your turbine blades, because delta will increase. And what we have predicted, I mean, we have predicted the temperature difference between the upper casing and the lower casing on the behavior of the variables. We are predicting that if we keep it running more than a 600 hours, it's going to cause a delta difference between the upper casing, lower casing, and then if you keep it running, because lower casing will have a less expansion and upper casing will have a more expansion, and because of this difference in expansion, your blades will have a wear and tear. And that means if you are not even actually working on my or taking steps on my prescriptive analytics, we are predicting that your blades will have a wear and tear. So that's called, at this time, that's called a predictive analytics. So sometimes we have a problem statement only for one. Sometimes we have a problem statement where we actually have to give all those three outputs to the owner, so to the customer. Sorry. So because customer will be actually very much interested also to know why it's happening, what will happen, and how it is going to actually work in future. So then when we develop, I mean, some preliminary models, and we develop, for example, we did clustering, we did regression, we did defective detection, we did I mean reinforcement learning or deep learning, whatever models we implemented. Or I mean, you most of people will be familiar about, I mean, classification or regression. I mean, for prediction mostly we use a regression. So we have to go in a validation phase. So validation phase, it's the phase where we actually validate our model, how well our model is behaving, and we go back to the data modeling. We again validate, we go back to the data modeling. But as I already told that these are back and forth steps. So at this time, we actually have to find out whether our variables are fine, whether what the data we got from the customer, or is it actually going to answer our queries or not. So if not, we have to completely loop back and go to the first phase again, to the data acquisition. And maybe we have to take some new tags initially, which we have never actually taken in my data set. So I mean, I'll further explain how we to go it in next slide, but this is actually brief what I'm giving here now. So then there comes the deployment and optimization. So unless we don't have a complete deployment chain for any project, this is just POC, proof of concept. This is not a project. So unless we don't know a deployment, where we are going to deployment, how customer is going to use it, how customer is going to pipeline his data to my model, and how model is going to actually give him outputs, and which regularly at regular intervals get updated. This is not a data science project, but this is a only POC, which most of the products are in our academia, which only lost to the stage of POC, and we never go to the deployment chain. And I mean, it's mostly my experience from it that most of the academia papers go to this phase where data validation, and when we try in the phase of a deployment, they mostly never work, because I mean, it's because of this thing, we never take in consideration that deployment. I say most cases, not everyone case. So if I go, I mean, where actually, but because the problem, I mean, the topic given to me is a data acquisition, and I mean, of its understanding. So I will actually say why data acquisition lies in this data science life cycle. So if we see here, so I mean, this slide is mostly defined by a Microsoft architecture. I mean, there may be different architectures, different people following. So this is one architecture which Microsoft is following. So as I mean, I gave understanding about hey how we are starting, and we should have a business understanding of problems, and unless we don't have a business understanding, we will never able to solve. And one more thing is here, I mean, everyone should consider is we have a number of future reduction techniques right now. For example, we have a PCA, principal component analysis. We have a lasso algorithm to, or we use correlation to decrease, but out of all these, the best one to reduce the number of features is business understandings. For example, if we get a data set of 1,000 variables, it's never possible for us to work with all those 1,000 variables. Not possible for any algorithm to give a best result with 1,000, even in a deep learning when we go a deep learning. So the best thing is business understanding, to interact with him, actually see from his interaction what are actually the variables which are going to affect my final analysis. So then we jump from this to the data acquisition. As I told, it's a data acquiring, data cleaning, preprocessing, these three phases. So if we see here now, we are in a data acquisition phase. So one thing we have to understand, data acquisition is not a one-step process. It's not a one-go process. It's not like we uploaded Excel sheets, 100 Excel sheets, or we went for some database system, suppose Postgres or anyone, and we uploaded it once and that's it. We take extract and that's it. That's not it. Because as I already told you that when we are actually doing this modeling phase, we may come up to the point where our tags are not actually enough, where our variables, where our features are not enough to define our problem. This is the stage where we have to go back. So this stage makes so much difference in our problem statement. So this stage is actually data source, pipeline, environment, and wrangling exploration. So what does these 4 blocks actually mean? So first thing, when I now have an interaction with the business people, and they gave to tell me that hey, we have this data. So my question should be, where is data? Is it on-premise? I mean, when I say on-premise, is it within the organization, or you have actually hired some third party? For example, is it on AWS? I mean, maybe they have in Amazon cloud, or it is on Azure, Microsoft cloud. So this thing is pretty much necessary for us, because what my and what every data scientist want, that the data should be very close to my modeling environment. So the first thing is to find out where actually data resides. If it's on premise, so okay, you have it on premise. So do we have enough compute resources to actually do our analysis on premise only, or actually we have to use some machine learning? Okay, I will not go into deep machine learning as a service, because I am going to give also some brief about that in few next slides. But here I'll say, for example, if my data is very away from my actual modeling where I'm doing my computing, so every time, I can't extract manually, go there, extract. So for this, I need to set up one pipeline actually, which every time pulls my data from the data source and sends to my model where I am training my model. So it can be actually streaming, one by one data packets, or it can be in a batch. So it depends. It can be very low frequency data, or it can be a high frequency data. For example, it may be medical data which is getting generated in enormous amount, every day. you will see lot of a data is getting generated, or it may be a very small data, small data sets. For example, health of a one system, how it is varying over the time. So it completely depends what is their generation. So this pipeline setup depends how fast and how small our data is getting generated. So then there is an environment. Okay, as I was saying, whether we have an on-premise environment or whether we have a cloud environment. Okay, we have okay, so there was some background. Okay.
Continue.
Okay. Okay, so now if we see, for example, we are working on a cloud, so then we want our data on to be the cloud, for example, data lake or any Postgres, Microsoft SQL, or Cassandra, or Redshift, S3, whatever will be the sources of, and it again depends on a data. For example, we have a graph data, so we want that to be in our Cassandra databases or in S3, which is given by Amazon. We have a relational database, so we want them to be pushed into SQL. So because at the end of a day, we have to act as a data science people. I mean, because most of people and most of the books you will see referencing data science as a intersection of a machine learning, artificial intelligence, and mathematician, or but they will never say, hey, we actually are the integration of a data engineers also. We are actually business analysts also. I mean, the data scientist should be a business analyst. He should have a communication skills to get the understanding of business. He should have engineering data engineering skills to actually see where data is, how I can actually pull data in my model completely. I mean, what are they actually the data types I need? So these are very essential skills which so data science, if I see as in whole, it's somewhere I mean overlapping set of data engineers, business analysts, Python, I mean I say software programmers, as well as a mathematicians. So it's somewhere sitting in front in middle of all those. So then we do exploration. So exploration again, I mean, as I say, it's completely data. Your data may be structured. For example, your data may be structured or unstructured. So for example, if we say we are taking images, we have to work on an image data set. So that's completely unstructured. I mean, we don't know what all images are present in my data set and how they are taken, what is the acquisition steps in there. But our data can be also sometimes structured, which is relational databases, which are mostly present in RDBMs. So we have to work with different data sets, different type of structuring of a data sets. So and some type data is just semi-structured. So when I say semi-structured, for example, if we are working on an NLP, so we may have nowadays in NLP we will never get a complete data set written as in a words, but sometimes what we will get smileys. And those smileys in present world, I mean, they actually have a lot of meanings. So people use expressing their feelings, those smileys. And now with the WhatsApp and all that Twitter stuff, now we can see not only smileys, sometimes people are using for home, they will use that small icon home. For school, they will use that small icon school. So data is very vast, and data, I mean, its veracity is very vast, and it's pretty tough to actually, toughest setup is this thing, to keep it its integrity, and to keep it, I mean, coming and doesn't lose any information. Because maybe in past, if we go few years, I mean, one decade back, so we was not that much concerned about the smileys, but now we have to keep them. Because they are, so for example, if we set up one survey for employees and we say, hey, are you happy with the present facilities we are providing you at our location of work? So most of the people will not say yes or no, but some will create smiley of weeping, some will create smiley of wow, and they are actually the sentiments of a people. So this part is pretty much tough, I mean, to consider what. So ultimately, after that, I mean, this is a back and forth. So we draw, we done exploratory data analysis. We saw, okay, some tags are missing, we go back, understand again business, bring again, do in a data source, pipeline environment and again do. And so that's why I was putting much emphasis on that we should have a proper pipeline, because if we doesn't have it on first place, we can never complete our problem statement on time, because this will take more time us again. So then after that we go on a modeling where we do a future engineering. For example, we do transformation of data. So I will not go that much into it. I mean, how we do, as I already told, for future selection we may use, for example, a correlation, and a simple correlation method we may use that two futures are correlating very much each other, so we don't need both of them. We can take one out of them, because otherwise they will add a model biasing in our, or we can simply use some visualization graphs, or maybe some hi-fi techniques like principal component analysis or lasso regression techniques, and say, okay, we don't need 100 features, we only can work with the, or we can use recursive elimination of a feature. So there are so many algorithms right now available. And
sir, can I ask a question?
Yes,
sir, whenever we have multiple features, we cannot find the correlations between all. So is there any technique to identify there might be a probability that these two features are correlated, so I can try correlation technique, or we have to try with for all? Let's say if you have 1,000 features, so for all 1,000 we need to find correlation or maybe some other things.
Exactly. This is the emphasis why when I was giving on my business understanding, you remember I told that even we have hundreds of techniques right now available to reduce the future set, but definitely this one is the best. So when I say this one is the best, so because as you are saying, hey, it's very tough for a human eye to go and look into the 100 of the futures and their correlation. Is it? It's your, I mean, it's very valid statement. It is very tough, but right now, I mean, there are the three answers to it actually. The one is first few variables you have to drop at the business understanding. That's for sure. I mean, no, unless you will not have a business understanding, you will never able to solve it, because as in for example, in my turbine, they give a airflow pressure. They said, hey, this is the airflow pressure, and you have to actually predict what will be the temperature after 100 hours. Okay, I have an airflow pressure, but can you please give me where are the locations you have put on a sensors? Okay, it's a circumferential, or it's on its circular. It is a circular, or it's a radial. So if it's a radial, so all the three will measuring actually the same airflow. Doesn't make any sense for me. Okay, it's a circular. It's on its periphery. Okay, it's present at X, Y, Z. First thing. Okay, I need all those four. If it's radial, no, I don't need anyone. I need first only, because all will be the same. Second thing is where we are saying that, okay, correlation. Yes, we can drop correlation. There are the few features we can drop with the correlation. Done. What our eyes are able to see in a correlation, we will drop them. But still, I said there is one very good algorithm, PCA, principal component analysis. So it actually finds out, let's suppose that, I don't know whether you are able to see my hands actually on camera. So let's suppose that we have one variable is in X direction, one is a Y direction, one is a Z direction. And we only want, out of three variables, we want it to reduce actually. And if you know that principal component analysis is never actually giving us back those variables back which we introduce, but it gives us completely new set of a variable. So what it is doing, it's actually finding in which direction it has a maximum effect. For example, if it was at an angle of 30 degrees to X, and so that means its more effect will be in X compared to in Y. And this okay yeah, one more I mean,
yes, sir.
There is one more technique, I mean, which is very much predominantly used in data science right now, is recursive elimination of a feature. So that's the one algorithm which actually, when you set up with all the 1,000, you give a target variable and you have 1,000. You take in consideration once. I mean, in order to understand in simple regression, we want to actually predict the salary of anybody. So let's suppose that we want to predict a salary of an employee, and we have a features like working hours, how good he is in a bargaining, what are his experience years, and actually where from he has studied his knowledge. So background knowledge. So let's suppose we have 4 variables, for example, and we finally predict its salary. So our target variable is a salary, and all those are predictors. So in this case, recursive elimination, when you initially set up, you model it, the model will not give complete, very good output. But one thing we can have in this, in recursive elimination features set, that's one algorithm. You can find it actually. It will give you actually the importance of weights, which all variables have very much important weights with respect to the target variable. Then those which doesn't have an important weight, it will drop them. And it will give you, hey, let's suppose you are right now predicting it the 15 variables, but what I found, only 10 variables have actually the very good weightage, and rest 5 have only 0.001 weightage. So those variables doesn't create that much difference in my final target variable. Does it make sense?
Yes, sir. And sir, can we say that the sequence, that 3 steps that you have mentioned, the sequence should be the business analysis, then the recursive feature elimination, and the last one should be the PCA, because once we transfer something to the PCA, all the dimensions will be changed, and with respect to the eigenvalue, we'll have the totally new features, and maybe out of that all feature, we will select some topmost entries. So can we say that always this PCA comes at the end, or maybe some other case?
Okay, so it depends on your problem statement. For example, when I say the recursive future elimination, so it may come sometimes before PCA. For example, if you are sometimes it may come after PCA. So understand this. I'll give you one real-time example. For example, when you want to give a prescriptive analysis with target also to your customer. For example, customer came, and simple example of this, my turbine is heating. I will keep it this example because it is relevant to this. And he wants also to know what variables are actually affecting it. At that time, you compulsory, when you create your final model, it should have all the variables, because you are very much interested in it. Okay, finally, my target variable is saying that wind, the initial airflow pressure on the left axis is more. You have to reduce it by 2 lbs, 3 lbs. So at that time, when you finally develop the model, you don't have to use PCA at that time to reduce it, because you want actual features. What are the features? So that you can tell him what are the features are actually affecting it. But sometimes you are not worried about the features, what features, how they are going over the time, but you are worrying actually only about the target. So at that time, you can apply PCA even after doing RCA, recursive elimination. Does it make sense?
Yes, sir. Yes, sir. Thank you very much.
Yeah. So after that, okay. So after that, when we do modeling, and then we go at deployment. So deployment phase is this is the phase where it may cause a customer acceptance, or it may not. If customer will not give accept, you have to go back. For example, I will give a simple example here. Let's suppose the same thing I said. For example, they want to see the turbine temperature. They want to predict a temperature of a turbine when it keep running for more than 500 or 400 running hours. So they will be very much interested in it, but they will not be interested only in a temperature. They will be interested in a delta temperature. What is the, so because if it keep running for a 1,000 and million of hours and it doesn't do any wear and tearing, so they are not worried. Keep it running. This is good for them. They don't have to put up people for stop and start of it. But if there is a difference, potential difference between the upper casing and the lower casing, upper casing has a more temperature, lower casing has a less temperature. That means in upper casing there will be the expansion. In lower casing there will be no expansion. So the blade which is present in upper casing, when it rotates and goes in a lower casing, it may has some wear and tear. So there they are not only actually dependent on your temperature prediction, but they more want the gradient. So irrespective of thing, even if you have 80 to 83% accuracy, which is considered very good accuracy in a data science, customer will never satisfy, because he will say, I don't. I mean, this has nothing, no value for me. I mean, you are predicting 82% correct temperature. What I want you to actually predict the delta, because delta is the something which is creating fuss for me, which is actually the problematic for me. So even if you predict with a 95% accuracy, but you will not predict the peak. So the peak is the one where actually delta occurs between the two. You will not predict the peak. He will not be satisfied. He will say, no, I don't like this. I mean, I don't like this because it doesn't create any value for me. I mean, for them, they are more interested in delta, not your predictions. So this is ultimate stuff. When the customer gets accept, done. Your boom, your model is in implementation. Okay. So now if we go on another step, so how to do actually, how to do it? I mean, how to do this? What is the goal of my ingestion? Because I mean, the whole life cycle is not in my, the topic assigned to me to discuss is acquisition, not the whole life cycle. So I will now, I mean, go in acquisition in a particular way. What acquisition? So the goal. So the goal of my acquisition is finally to produce the data, or you can see the high quality data set, which my target variable or which my model can use. And the second goal is this, I mean, which I completely put a lot of times emphasize, is that this data should be regularly updatable. It is not only a one time, because this, as I see, this whole is an iterative process. This goes back and forth multiple times. So we companies should have an architecture data pipeline to set and to bring the data from data source, to put it in the environment where my model is training, and to put the data again in that environment where I have to deployment. So it should be. So in short, it has a three steps. First is ingest the data. Second is explore the data. Third is set up the pipeline. So when I say ingest the data, so as I already told, ingested data where in my target environment, where I am actually, where my compute resources are. For example, for right now, the people who are working locally, for them their compute resource is a local computer. So they want their data, maybe even if it is in an Excel sheet, and they have written some small script in some database. They have in some database server, and they have pushed that script, and that script is pushing regularly new Excel sheets in your local machine. Okay, we are good. That's a pipeline for that. But no, in real world, we actually doesn't have simple that. Let's suppose at we have a turbine installed at some ocean shore. Okay, now on ocean shore we have a they have some local collection of a data, but we don't, that local collection of data doesn't mean anything for me unless they doesn't have a one proper pipeline set up from that ocean shore to the AWS database where my compute resources right now present or where I have to work. So every time, so what I will do in that case? In that case, I will write some Java servlet, or I will write some Python service, or I will write some simple. I mean, you have a lot of actually SQL commands and talent. For example, talent is a one such a way. I have a talent server there. I will install talent server there and say whenever new data will come, just push this new data to my AWS location, and I will give, for example, S3. If it's a grab data, if it's taking images, or I will give Redshift, or I will give, I mean, different sources. Or if I want to push it on a Microsoft, I will give Azure location, because there I would have a Azure. I mean, everything will be stored on Azure. So the second case is exploring. Okay, now the data I'm getting, is it actually the data which we really need? I mean, what are actually I can explore? What's the quality of data? What, maybe there will be some noisy data, there will be some missing values, there will be some discrepancies. For example, let's suppose that we are taking a weather forecasting data, we are taking a rainfall every day, and we have to actually predict the rainfall. What will be the rainfall? I mean, we have to forecast actually the rainfall in next year. So it's not. I mean, definitely you will not get rainfall every day, but you want to predict rainfall every day. What is the rainfall? Maybe sometimes it will give very, so then you have to deal with those missing values. How you can actually do that? Maybe median, mode, or different central tendencies or percentiles, or I mean there comes a statistics, or you can use some statistical terms to come up. I mean it depends completely on your problem statement, what type of a problem statement. For example, sometimes you can go with a mean for a missing entries, but sometimes mean doesn't work for you. Sometimes you go for a median. For example, you have an image and you have some missing pixels, and you don't want them missing, and you have to actually, so you can't go with a mean because mean may create a false images. So there you will have a adapt to thresholding, or you can have a different things. I mean, one thing is how you can do then this adapt to thresholding on your image. So this is one. I mean, this is one completely different section where these things can be divided. I mean, these things can be explained in a detail how to do that. And then there's a setup of a pipeline. I mean, what is the motivation? Why I'm doing? Because if we do to our data analytics service, we send a data which is a garbage, definitely we will get a garbage out. I mean, it's a very good term used in a computer science, garbage in, garbage out. You have bad data, you will have a bad predictions, you will have a bad prescriptions. You will never, and this is a famous saying. People who want ML and AI really just need a linear regression on a cleaned up data. So if you have a completely clean data set, you just doesn't have to do anything else other than you have to use a linear regression, and you will come up with a very good result. I mean, this is saying, I mean, I'm just want to give how important the cleaning of data is. So now where this data is, I mean, where this data is. So it may be in-house, it may be open data. Okay, this is pretty much very much useful for us. I mean, this, if it's in-house, it's very much useful for us. When I say in-house, so in-house means, for example, I'm working in an organization and we have most of data in-house. So in-house means most of our services which we are giving to different customers, they are using our services. Most of data from those services which get generated, that is present on premises for our database. For example, GE have its data center in India, in Bangalore. I mean, Global Research Center. They have its data source in USA. They have in China. So how it's important, because it's the fastest way to start. You will quickly start. You don't have to search here and there for a data. You directly know where my data is. Okay, it is in Bangalore or USA. I can directly, because it's in-house. So most of the time you don't have to go through the. Okay, this point I want to emphasize. So privacy is very, I mean, very huge thing in this, and it's the thing which everyone have to consider while working on a data science project. It's not like that you can go anyone and take any data set and start working, and after completing the problem statement, they will come, it's my data set. How you can use without my, I mean, without at least asking to me. I didn't give consent for this. So you don't have to go those things even you are having an in-house database. So restrictions may not apply. And the best thing is you can talk with the creators of the data. I mean, for example, there is a lot of information stored in the metadata. So you don't have to actually pull your head against the wall. You don't have to do that much research. You can directly go, you can talk with the people who are actually the creators of the data. You will say them, okay, this metadata, what it refers actually. Can you please tell me what is the importance of this tag? What does this tag mean? What does this XYZ tag means? Can you actually tell me how it's getting generated? So you don't have to actually push a lot of emphasis and lot of effort at the places. I mean, how it is generated, why it is generated. So these are the very, I mean, these are actually the benefits of in-house data. But as we see in our academia, mostly what we work on, we never get the in-house data, and it's pretty much evident for us. Why? Because we are working on mostly social data, the data which is readily available to everyone, and we are actually, because the first thing is in-house data, the companies are mostly working on this because they have company-based problem statements. But the statements or the problem statements which we are dealing in academia are mostly mostly the problem statement which whole world is dealing. I mean, we are trying to generalize for the whole world. Okay, this technique, that technique. Now the data that is free and free to use. This is the open data. Okay, this may be the government data, this may be the science data coming from the experimenters, AdStrand, this may be the social data, for example, WhatsApp, Facebook, Twitter, all those things. I mean, these are actually the social data. Now, in this data, there are few downcomings, like you have to clean the data. You have to clean the data, and this data cleaning is very tough because social data, as we know that as it's readily available, it's a free so generated. It's not then generated by experts. It's definitely generated by the people like you and me. So we are not expert in a data generation. We can generate the data in any way. I mean, it's our will. We can write in Excel sheets, we can write in a text files, we can write in flat sheets, spreadsheets, Google Sheets, anything. I mean, we are not expertise, so we can't generate the data with a view, okay, someday some data science people will come and work on this. So it's very messy. We would have a pictures of a dogs with cats, and we would have our pictures all together mixed in a one folder. So we don't care about sorting even them. So this is the open data. But now because mostly we are using open data in our academia, and sometimes we can't even afford the in-house data because it's very costly. I mean, data is like Zaman sir earlier said in the first session of this program. He said that data is like oil, so it's like oil, and it's much costlier than oil. So I will give, I mean, the people who among you are pretty much interested to go with to do data science work and need some free data sets. I mean, they want some data sets where they can get a free data set. So I have actually compiled some of the sources for you. So first is at www.go, and it's the US official data. So this site you can go. I mean, you can visit this site. It has nearly 224,750 data sets. And mostly when I do some, I mean, this is the site which I like personally, because when I do some exploration analysis and I want to actually test a few things, I go this site and pull up data set from any. I mean, it has a, I mean, the people, I mean, this US government have very well maintained this. It's an official website for the government. And you will see they have a separate fields like agriculture, climate, ecosystem, energy, local government, maritime, and ocean. And one, I mean, the likeable is this health data. So they have a lot of health data there. You can go and you can actually visit this site and get the data sets and start working on them. So the one thing is here, it's you don't need any license and any other thing. You can get this data anytime. The second is for the same type of data go dot. If you replace this UK with .in, so you will get the data for India. But I don't know. I mean, maybe even if you go that, you will see a lot of data sets are not maintained properly in .in. So, but still, you will get data to work on. And then there is this business and I mean, for UK, United Kingdom, like business, economic, government. I mean, you can go and you can take in any data set. What is your actually interest? You can go in that very field and start working. So another actually is for Sweden. Sweden is this sites. I mean, if someone is interested later on, they can ping me on my. I mean, I will give finally my mail ID. They can ping. I can send you those addresses actually. So these are compiled so many addresses for that you can start working. And this site is, I mean, I can call it boss of all those sites. So this is like a boss. I mean, it's tracking city data of mostly all the governments present in world. So it's called as a global open data index. And it not only this site will give you actually the indexing. I mean, how good data any country is. I mean, for example, Mexico is they're producing very fine data, and then it can rank also the countries on that basis and give you the data sets. So you can go again. So then there is, if you are very much interested in a scientific data, so you want to work on a scientific rather than this climate and all that stuff, you can go on this worlddatasystems.org. So you can get a these sites are pretty much important, and you can actually share these sites with your students also in class, and so that they can get a open data, so they don't have to actually move here and there. So then
can you share the link again? where we can get the data, public data available?
Yeah, these I'll compile these and I'll send to the Jahangir sir, and maybe he will send to every one of you. And these are actually the sites from right from this. When I said it's for the US government, this is all this data is open from exactly from this site. I mean www.go, and from this site www.go.uk, and from this for Sweden, and this from this you will get for every government data for every country of the world. And according they will index also. I mean that's a good thing, they will index data quality and all that. Then there is a world data system, you will get a scientific data of experiments which are happening presently in a world and all that stuff. And these are some sites again. I mean I have you are interested for a time series data, so you can get from a Google Trends. So you are interested for open science data, you can go here.
Screen.
Oh, you are not able to see my screen?
No, we are not able to see your screen.
Oh, I thought you are able to see my.
From past 2-3 minutes, we are not able to see your screen.
Okay, let me share again. Shit. I thought actually, I mean, you are able to see my screen. Okay, my bad. Now you can see?
Yeah, now it's.
Okay, search. Okay, now you can see.
Yeah, it's visible.
You can take screenshots of these. I mean, you can take screenshots of these. So one is DataGo, one is this datago.uk, and then is this for Sweden, and then this is I mean I'm very much fan of this website because you will get most of the data and the quality of a data. And then this is for a scientific data if you want to work on a scientific. And these are some I mean compiled again. I mean you are interested in, so then you can take also data from these like science data. This is again science data. This is sent for open science, and this is for a Google Trends for mostly for a time series. And there's also one thing that's Google Correlate. I don't know how many people have among you have used this. This is the new launch. I mean it probably happened in the last year or so. So where you can actually search the popularity and trends, and you can correlate them. I mean these aren't just drag and drop things. So another thing, how you are getting data, maybe because from APIs like hashtags. So you want hashtag World Cup win by India. For example, you want cricket data and you want World Cup data. So you can directly use Twitter APIs, and you can get data with the hashtags. So I mean, for most of the people, those hashtags are just to highlight the events and all that stuff. But for us as a data science, those hashtags are very helpful because we actually get the data for a particular event. And then this scraping of data. I mean, this is pretty much interesting and pretty much the field where a lot of work is happening in present day. Scraping of data. This is the data where actually the people are not actually making the data in order to actually use for a data science projects. So here we need our effort to scrap the data. For example, presently. I'm not sure how many people of you are aware is one project going on that's called Public Intelligence Al-Zatari project. So it's happening in Syria, where people are living in those tents. So because we know that their life is pretty much bad these days because of the war going, and now they have arranged some type of tents for them. So what they want to actually have some government policies for those people living in there, but for that they need to know exactly the position and as well as the spacing of a tents. So they can't actually go and now measure each tent one by one and all that. So what they did, they took a satellite pictures of this, and this is called as scrapping because we are scrapping data from websites, from maps, from anything. So they took the image of it and then scrap the data, then actually create different machine learning, artificial intelligence, I mean algorithms in computer vision mostly, and then they measure actually the pixels rather than measuring the tents. They measure the pixels which are actually showing the location of a tents. So this is how they got the difference or the difference between the two tents, how a tent is located, what is the spacing between the two tents and all that stuff. So this is pretty much good. I mean, you can also use this. For example, you can go and do scrap from using different tools. There are web scraping tools which we are using. So another thing is now sometimes you get a problem statement, but they don't have a data at all. So that is a pitfall for mostly. But then you can tell them, okay, if we want to actually do work on this problem statement, we have to go through some collection things where we can collect, for example, natural data. You can have informal discussions where you can return up them. For example, they want you to say the employment satisfaction with our new policy. So you can actually meet up to the 100, 200 employees and you can have an informal discussion on them. You can pen down them and then use NLP on that. You can have interviews. You can have a surveys and a minute survey. Are you really satisfied with the new facility provided by office or not? You can have a yes, no. You can have a polls, A/B experimenting. So A/B experimenting, like, I mean, everything keep very simple. You are interested, yes, no. You want to go to the picnic, yes, no. So even we are doing it in a daily practices, but sometimes we may even doesn't realize that we are actually doing data analysis. So we are saying students, how many students want to go for a picnic? So 10 students say yes, we want to go, and 2 students say no, we don't want to go. So then you are saying okay, because 10 are saying the highest probability is that highest number of people are saying we will go. So this is actually where you are actually adding a classifier on them. So you are adding yes, no classifier, or you are adding a binary classifier on that. So now there is a passive collection of data. So sometimes we are actually a source of a data and we don't even know. The one simple example is a photo classification. All the day we keep taking photos and then hashtag my home, hashtag beautiful home, hashtag homemade on a mountain. So actually we are nothing. We are a node for a data generation for them. So we are giving them lot hashtags and we are giving them, and that's a photo classification. And autonomous cars, you may be very much aware these days. I mean, autonomous cars, so they are collecting data. For example, we put an autonomous car on a road, and it's actually collecting data. It's collecting angles. It's collecting what are the turns. It's collecting different traffic signs. And sometimes if we run it on a roads in mostly in subcontinent, we'll see a lot of the things which we never see in a Western country on roads. So again, it will collect the data of that also. So health data, for example, people are wearing wristwatches, and I have for example, I have a wristwatch. I have a Samsung device, and I have that AQ health device installed on it. So every time I do exercise, I am actually collecting my heart rate. I'm collecting my fat burn. I'm collecting my exercise time. So actually, if we see, we are also nodes in this world where I'm a data node actually, and a lot of data is being collected from me. I'm uploading my memories, my work, day-to-day work on my Facebook ID. So everyone is actually collecting my data. They are knowing me more than what I know myself from that data. Okay, and that not only that, they know even my intuitions. They know what I'm going to do next after this with this all the data I'm generating. Now self-generated data. This is the pretty much useful field in present world. So self-generated data, I mean, most of the people are right now focusing in it. So self-generated data, if I say, it may be external reinforcement learning, it may be gains, or it may be internal reinforcement learning. Now, if I say external reinforcement learning, for example, you know that when kid born, I mean, he start walking in early days. So how actually he's getting to learn? Okay, for example, he's going to learn this is a switch off and switch on, where I have to off the lights and I have to on. So if you see somehow when kid is doing some good activity, we are actually encouraging. Okay, you done good job, you will get a chocolate. And when someday he do some bad activity, we say, no, you didn't do a good activity. If you do again this, you repeat again this, I'm gonna beat you. So when this thing is coming, so you are actually encouraging him on a good moves and you are actually discouraging him on a bad moves. This is exactly mimicking in a reinforcement learning, where our algorithm is encouraged. It has been given plus points if you do a good activity, and where it has been discouraged or if you do a bad activity. For example, I put an autonomous car on a road. It's running on a road. It's fine. We are good with it. For example, suddenly it has a stop sign. Sign. It's a stop sign on a road which is written on that board. It stops. Good. We give it a plus. Okay, you stopped on a very good position. I mean, you are supposed to stop. Okay, plus it. So algorithm learns. Okay, I got encouraged. Now, how it's happening? These are actually the nodes and all those neurons. I'm not going that deep, but I will say we give it encouragement. We give plus point. We say error is decreasing. Now, next time this car is again going the same route, and because I know that it stops when I show that stop sign, I falsely put not a stop size, but I put maybe the board of similar color, that yellow color, but not written stop. I write welcome in that with a red. But let's suppose that right now it doesn't actually process in a good way, and it again stop. Though it was the, I mean, I fool it. I personally fool it. I mean, but it doesn't. It actually stops again. So that means it did a bad activity right now. I don't want it to stop. So at the time I decrease its merit. So I penalize it on a bad moves, and I give entailments, or I encourage it on a good moves. This is how reinforcement learning is working in a present day. Then, but this type where I use external things, this type is called external reinforcement learning. Now another step is internal reinforcement learning. So for example, I don't know how many people of you have played PUBG. So if any one of you, I mean, a fan of a video games or like a PUBG, you would have seen that when it started in a season 1, 2, 3, or 4 seasons, because right now it's in probably in 14th season. So when there was a season 1, 2, 3, 4th season, you know that there was a bot. I mean, there are the actual players fighting each other in a battlefield, but there will be also the bot are fighting. So if you see at that time, those bots were very inactive. I mean, they can't even shoot anybody. They come there, they stop at one place, and they get shoot down. And I mean, the real player got a very good kill count. So, but with time, how they actually made it very good, they introduce internal reinforcement learning in those players. So if next time that bot got killed, like without moving, so we reduce its points, and if he move little, we increase its points. So continuously over the iterations. So it's not a supervised learning. It's not either unsupervised. It's somewhere between supervised and unsupervised. So that's why it's a reinforcement. So I'm saying at that time, I'm actually now with time those bots learn to the extent that right now they are actually killing the actual players who are actually human bots. They are actually killing them. They are not. I mean, to that extent, it has improved over the time. So, internal reinforcement learning. So example is PUBG. So another very good example, I mean, for the GANs. Now I'll say what GANs are. Example, CT scan data. So GANs is actually a neural network. I mean, if we in a simpler terms take, it's a neural network. So, but what happened in GANs? In GANs, there are two neural networks fighting each other. So GAN is generative adversarial neural networks. So we present in a present world, we are using them to generate the images. The images generated by GANs are very much similar to the humans, or whatever we give it to the data set as an input. They will generate output images very much similar to them. And I mean, for our it's surprising, for everyone's surprise, those images may be the characters which we never have seen in this world, but they are pretty much looking like those. For example, I give 1,000 human faces to a GAN. It will generate one new human face, which will be a human face, but we have never actually seen that in this world, but that will be. I mean, this is the power of GAN. So how it is actually working? So it has two parts. One is a generator and another is a discriminator. So a generator, you can take, I mean, in a simpler words, it has a neurons or a neural networks, and each neuron is actually learning one or other feature. So for example, we know if I say image of a human, so we have a features, we have contours. I have ears, I have eyes, I have eyebrows, nose, lips, all those stuff. So every one of these, it's actually, if I say it's curve, these curves, these pixel intensities, these variance in a pixel intensities, these 3D variance in loops, all those comes as a features. So what happened? Those neurons keep remember those features. So like they decode. I mean, if we say they type of a decode at each level. For example, now if we put a 10-layer deep neural network, so at the 10 layers they will decode at each layer. They keep decoding this. I'm saying in training phase, they will keep decoding it, decoding it, decoding it, and in each phase, in each layer, in each neuron, they will keep one or other future state. So now, what happened when we give a randomize, and that we called in our terms we called as a latent vector. When we give a latent vector or a latent space vector, it may be it is a random wise nice any random array, numpy array. As soon as I give only random numpy array, because I already have a neuron layer set up 100, 200, 300 layers, depends on my neural network. Each one now decodes back, because earlier it decode, each one now encode back to the extent where it will generate exactly the image. But you know, because we already said that we are training it on 1,000 of images, so actually the information stored at each node is probabilistic function of each of these 1,000 images. So we have a probabilistic function stored in each node. Now when we are actually encoding it back, it will be multiplied by that, or which is called in this term as a weight. It will be multiplied by that weight, and it will be actually by that probabilistic function, and it will generate a completely new image, which is actually the merger, or you can say somehow probabilistic function of all those images, and we get a new phase. So but now how it is getting trained, so there comes the discriminator part. So discriminator initially is very naive. I mean, he's like a stupid initially. He doesn't know anything. Initially he's very intelligent, very much intelligent. So he knows, for example, you when pass a real image to it, it will give 1 to real image and 0 to fake image, because initially fake image is nice, so it can directly say it's a fake. But with time, when we keep it in loop, we will keep making this discriminator stupid, and when it gets to the stupid to the extent where it is not able to find whether it's a real image or whether it's a generated image, we say that our generative neural network is trained. And in this way, we can say, okay, I have trained it to the point where now my discriminator is not discriminating between the real image and the fake image, or we can say that training loss have reduced to the minimum. So now how this is happening in a real world, that's one more discussion. I mean, but it's very much commonly used field right now. So I don't know how many of you you know that the cloth industry is pretty much working in this. So cloth industry, how for what they are using it, this they are using styloganes. For example, I have a red t-shirt and it has, for example, I have a red t-shirt and it has a flora of a white made on it. So I want to look, okay, if I had this black shirt and flora of a green, how it will look like. So rather than going in a Photoshop and spending days on that doing this thing, I have right now styloganes. I can give it to the stylogane, and stylogane will come up. I just give a legend, color legend, that I need this type of a color. It will generate me that type of, just to train. Okay, so encoder decoder are closely to it. So one more, I'm putting a lot of emphasis on this because this is a very much in use right now. So one more thing, you don't have enough training data. For example, you want to see, let's suppose that you got 1,000 images and you have to actually analyze for some defective analysis you have to do, and you only have the 15 or 20 images defective. So this data set is initially it's a biased data set, unbalanced data set. You can't do analysis on it. So how we can overcome this? Their gains come in for our help. So we will actually give those defective images to it and change their location, the defect, change the location of a defect. Sometimes put at x1 y1, sometimes put at x2 y2, sometimes z2 x2. So we will keep relocating this and keep our generator generating new images. So ultimately we will reach the point whatever number of images we want, and the fancy thing is that it will duplicate that defect at the different locations and even to the location where human mind never can think. I mean, it will generate such type of images. So this is the field I am actually working right now. I have a CT scan project where I'm finding for a defect in CT scan data. So because otherwise that operator has manually to go and check 2500 images to find out a one defect for a one part of, I mean, in next slide when I'm sorry, in next session when I have to practically show you, there I will tell actually the whole detail how that is happening. But here I can say you that I'm presently working in this field of a neural network, and so I know that this is very much important for us to work on this the gains and to generate data and to generate some fancy characters also. So you may have, I don't know how many of you have seen that these days you can see there are a few apps available where we have that OCR, object detection of a face, and then they are actually modifying the face with some completely new character. So those all things are happening with gains and object detection OCR techniques. Okay, so now after when we have all this data, I did this, I generated data, I have a data in my place. So we finally reach to the derivation of rules. I mean, what derivation of rules in our case is actually called as the analysis. I mean, so where you set up some model and you will actually, so now they may be explicit or they may be implicit. For example, explicit rules, you can in simple terms say the human mind can think about that. For example, what I was saying earlier, we want to actually predict the salary of some employee where he is working, and we have only 3 features to predict. For example, years of experience, his bargaining skills when he meet to the manager, how he bargain, how he present himself, and hours work in a week. So now here I want to put emphasize on two things. I don't know how many of you actually somehow saw this. I have written bargaining skills. So bargaining is not actually numerical value, it's a categorical value. Bargaining, I mean, he is a good bargainer, he may be bad bargainer, he is somewhere middle, or he is very top. So here comes how one more technique in a data preprocessing which we have to use. We have to somehow convert those categorical variables into the numerical variables. So then how we are converting these numerical variables into numerical variables, it depends. For example, in this, if we have 5 categories for a bargaining, high, low, medium, so then we can say low is a 0, high is a 1, and median is a 0.5. We can convert like that. But sometimes in NLP, you will say we have 1,000 of words where we can't directly use. So at that time is for our rescue is coming TDF, term document frequency, inverse document frequency, IDF, TDF and IDF. So that's how they are converting our simple written statements into the vectors. So whenever we work with NLP, we actually use term document frequency and inverse frequency. So IF, I mean any term frequency. For example, we have written a document on a dog, and dog is a strong animal. It has a good sense of smelling. So all those steps. So now we want to see the documents which are again written on a dog, and we have to pull out only those documents from my huge bunch of our database. So how I can do actually? So first thing is we have to convert those all documents into a mathematical representation, because after at the end of a day, everything is a mathematical representation or statistical representation. We have to work on a mathematical laws. So at that time, what we do, I will actually convert my document into a vector. And how that is happening? Using TDF, term document frequency. I will count. Okay, dog is used 100 times. So in one document, and greater than, for example, articles A and they are used multiple times. So their document frequency is very high. And when we divide it to the inter document frequency, it will go very low. So by default, it will drop all the articles. So it will say article doesn't have any meaning for us for object this when we directly go for a matching without sentiment analysis. Now when we go in a sentiment analysis, at that time articles create a value for me. So at that time, that's one more field when we go sentiment analysis as well as semantic analysis. When we go only for a semantic, then at that time we don't consider sentimental analysis. So this is, for example, I mean now when I'm here and I want you to actually I mean people they want to say, okay, so what is my salary? Okay, I got I mean into that. Now coming back to this, so salary, he want to predict a salary. So for example, here is an explicit rule. I mean you can easily imagine these hours of working greater will be the bargaining skill good. He will actually had a more salary. More years of experience, yes, more salary. So all the they are all those which imagine, which one human can imagine, human can emphasize on them, human can create a map inside his mind. It's a 3-dimensional data set right now, but it's pretty much evident for, I mean, I can say that it will every time show a upward curve in my graph if it's increasing. But now implicit is a set of rules where actually human mind fails. For example, I want you, I mean, if you, I mean, think with yourselves, I want you to say, hey, how you are actually doing. I know that these two dogs are from two different races. Okay, so, but how you, I mean, can you actually think with your minds and say how we are actually differentiating between these two? Okay, so if I actually put emphasize, I'm saying, okay, I see their eyes are different. The future above the eye is different. Their ears are different. Their cows, even if you see, they have a different nails. For example, it has upward nails, and bit of type it's downward moving. Their muscle structure is different. It has a short muscle, it has a long and strong muscles. So when this type of future is comes, I mean, where human mind can't even think, so we can't take dependency between the multiple. We can think when I take each in a one-dimensional space, but as soon as its dimensions increase, human mind fails. We can't even think. For example, I say now in this we had only 3-dimensional space. We can easily think, but here that dimensional space increases to the extent where my mind actually fails. I can't actually I can imagine to the 3-dimensional space, but I can't imagine when the dimensional space is pretty much high increasing. So at that time, this type of rules when we generate, those are called implicit rules. So in explicit rules, exactly like a linear regression can solve our problem. We can implement linear regression, done. We can predict the salaries. Implicit rules like neural networks, where the one first layer of a neurons and the second layer of a neurons are dependent each other, not only dependent on each other, but there is an interdependency of a neurons, which in our normal life we can't think of that because we can't create that interdependencies. We can take a 1-dimension, 2-dimension, 3-dimension independently, but we can't take their interdependencies in my mind. So that's why I can separate this dog, but this is my neurons are doing, not I can imagine like now. So this type of rules is called as a implicit rules. So tools for analytics. Now we reached to the point where actually we have an acquisition of a data. We generated some rules, and we want actually to put emphasis now what tools we are presently using for our analysis. So first thing is applications. So the commonly used tools is applications. Okay, so under applications, if I see spreadsheets. Okay, so spreadsheets, this I mean, most of you people doesn't have even realized that they are already doing data analysis, and some people already among you know that they are doing analysis using Microsoft Excel. So when I say Microsoft Excel, so you are doing median, mode, grouping, clustering, highlighting some things, undo, and sometimes you put some filters, and you even do the classification there. I mean, for example, okay, this is for the boys, you put a filter for a boys, you do classification. This is for a girl, you put a filter for girls, so you even do classification. And sometimes you do you unknowingly do predictive analysis there. For example, you see you sometimes put a filter in a ascending order, in a descending order. So you see when this thing is ascending, this thing is also ascending. Okay, money, salary for a some, suppose this is a hypothetical situation, salary is increasing, he is making a bigger house. So for example, hypothetical situation, it's not like that, but at the time you are even doing predictive analysis in Microsoft Excel, and you don't even know that we are doing Google Sheets. So, and one good thing about these, I mean, they are limited. I mean, their analysis is limited, but one thing is that they are universal in use. Anybody can use it. It's not necessary for them to be a mathematician, or to be, because we can know that people from arts streams, people from other streams are using. So it's pretty much like a tool which everybody is using. So this is called as a spreadsheets, and even Google Sheets are providing with the same things. Now second is SQL, structured query language. So I don't know how many of you are familiar with this, but again, structured query language is also doing primitive analysis on its own. For example, select students where marks is greater than 100. Okay, so from a table students, you are selecting only those students where marks are greater than 100. So you did already classification, good students and bad students. You already did that analysis with using a structured query language, and I mean, we even don't know. Okay, group students by age. We again already did classification on, we classified them into a different classes on the basis of age. And these things are primitive. I mean, I can say primitive analysis, but yes, possibly do with the help of query language. Okay, select all the rows where age equal to null. So okay, missing value for a null. I got missing value, so I did pre-processing with it. So even I use this SQL for pre-processing where value is null. Okay, and replace with 10, 5, 4. So anything. So we also did pre-processing with the help of structured query language. Now visualization tools. So the tools with which we can actually visualize, and we can also do some primitive analysis like the Tableau. Tableau, I mean, for exploratory EDA, exploratory data analysis, I find it very useful for a visualization techniques, Tableau. So in Tableau, you can actually, the best thing about is you can actually have a connection with any type of a database presently available in, whether it's a Postgres, Microsoft SQL, it is Excel sheet is comma separated files, that means CSV. All those connectors you can see in Tableau. Directly go in a Tableau, push the option of a data sources, and under that data sources you will see all those, in a drop down you will see all those options available for, and directly you can go anyone where your data is available. And even one good thing, you can directly go to the, not only local, you can go to the cloud. You can give the credentials of a database, and it can pull data from a cloud to your Tableau workbook, and where you can work on it. After that, there is a QLIC, similar to type of a Tableau, but little older than Tableau. And then you can get all those options there. I mean, I say even in Tableau you can go you can have a forecasting techniques there. For example, how many of you have used ARIMA? I don't know. The ARIMA is auto regressive integrative moving average model for time series time series. So you can have a direct tooling for this ARIMA in Tableau. For example, you pull your data, you put a time series, pull your time series data in your Tableau instance. You can directly use this ARIMA model on that. And good thing is you can change because we know that in ARIMA we have auto regressive, we have integration, and we have moving average terms. So we have 3 types of terms, and you can change. You can create 2 1 2 1 to 1 1 2 3, all those type of models. Second differential, first differential, 2 moving averages, 3 moving averages, everything you can and you don't need to be data scientist for that, because anyone can do this. It's a drag and drop tool. So I have worked on Tableau, so that's why I need to know. And maybe if you people start working on it, you need a license. And for Tableau, I think I suppose probably it's free for 1 month, and it has a different version, like desktop version, like Windows desktop version, server version, and one is for individual use. And desktop is it also provides you some server space with it. If you are, for example, 5 people are working on the same Tableau and you want to publish it, then to see for 100 of people, you can actually publish it on their server. So they also give a Tableau server where you can publish it. So then there is a Q-Link, which I told is and the very new tool in this is a web analytics. So web analytics is such a tool, and according to one analysis in last 1 year, I mean in 2019, there were only 15 resources available in India for web analytics. So it is pretty much useful. And if I give you one exact figure, Salesforce had one opening for this web analytics, and they were not able to even find that for 6 months. And after 6 months, they got the first, because it was pretty new and people were not aware about this. And now it's a booming, and now so many people are doing work on it. Then there is a Spotfire. A lot of industries are using right now. So now if we go for the languages, so languages are Python, Scala, Java, Julia, and MATLAB. So I mean, out of these 6 languages, I can't comment about that much about Julia and MATLAB because I have never worked in those 2. But I have worked on Python, or Scala, and Java. So if I say if I personally recommend that Python is a very much, not only because it's a general purpose language. And what it makes different from R is because R is a specific purpose. When I say specific purpose, it's mainly for a data analysis only, where you can't do a good development in R. It's for analysis, where and it has a support for statistical libraries. It has a support for mathematical libraries, but all in all, I can say it's a very good for statistical graphs and all that stuff. It's not a good for a full-fledged development. Whereas a Python, I personally like it because it has a lot of support available from open sources also. For example, whenever you had a problem in Python, you can reach out to the thousands of people right now, and because it's mostly people are working in it. And second thing, you will have a lot of deep learning platforms available, deep learning frameworks available in the Python. For example, Keras, TensorNet, TensorFlow, PyTorch, all those things, MXNext. All those are very much available in Python, and it's scalable language. Then we call Scala. Scala is pretty much fast. It's very good, but again, if someone wants to use a Scala, he should be very good with the Spark. So he can be he should be able to create a partitioning of data and all that stuff. And Java is good, but you have to code a lot in Java, and you don't have most libraries available. And for me, personally, I say that the language is best when it has a lot of packages available, because every time I will not go and write k-means from scratch. For me, it's not that much important to write k-means from scratch. I'll be more than happy if I just have to pass some estimators and just have to do the parameter tuning. So for that's why I say Python, because it has most of the right now available. So then another thing is machine learning as a service. So when I say machine learning as a service, this is one of the techniques or technology right now most of the industries are using. So for example, you have a huge data set. I mean, what one person, I mean, I'm saying at the personal level, most people, 95% of people doesn't even actually manage to buy a high-end laptops. And when I say high-end laptops, I say those laptops which cost more than 5 lakhs. So those are called high-end laptops for me, because if we go for a Tesla V100 GPU, which most of the data science and the deep learning centers are using, that itself cost is nearly 4.5 lakh probably. So we can't afford. And now let's suppose that right now the data set I'm working on is a 600 GB data set of a CT scans, and one TV Tesla V100, boom, it's failing, it's not even working, it's getting out of. So we can't afford all those compute resources on own to buy, and we can't afford to buy a 5 lakh rupees laptop and every time work on that laptop. And because sometimes even that is not specifying my requirements. If my for academics, maybe sometimes that may, but sometimes you will get a big data set also. So keeping all those things, so we should also know about this thing as machine learning as a service, as I already told that I am going to give a brief about it. So AWS also have a machine learning as a service. So they are providing a service where you can do a machine learning. So SageMaker. So what makes actually machine learning as a service very much useful for us is that they are providing us data at the same environment where our services are. For example, if I use AWS, Amazon's web service SageMaker, SageMaker has S3 with it. I mean, they will give you S3 space and they will give you EC2 instance space. So you can actually push your data in S3. You can do different type of things in EC2 instance, and they can give you a glue, they can give you a Lambda service. So for example, you train your model, you push it, you don't have to worry that much. You can actually go and configure it in a Lambda service where you can actually trigger it every time new data come. You don't have to actually worry anything. You can have a trigger set up in a Lambda service which can trigger your model and retrain and then validate and push it back. So this is complete orchestration. They give you a complete orchestration. I mean, I don't know, earlier days we used to go for a complete orchestration, we used to have a different tool like Jenkins, Airflow, DAG. So we had to go all those through tools and pull up, but they have given complete orchestration here also. And one thing, they are actually storing your models at .jar files and or tar files or gzip files or .pth files, which you can actually, if you are not interested anymore working on a SageMaker, you can actually pull them in our local and push them at any, because they are you can have to do a light weighting, not to go like for the heavy weighting which we earlier used to go. So that makes them very useful. And one more thing, compute resources, they charge you only when you use. You get charged. For example, I use 4 GPUs while training only, and then I can't use GPUs. I can do inference part on CPUs also, so I don't have to pay for GPUs. I can release those GPUs. I can say that it's elastic. You can use elastic compute resources, or you can actually configure for more resources only at the time of running. And one more thing is which is very much important in this for SageMaker to understand is that when you do analysis, at that time actually you can use a lot of predefined algorithms they have already in their containers. And when you push for a training, you don't have to wait for a training to complete, then only you can work on a new instance. What happened locally in a Jupyter notebook instances, so you have to wait other than. But here you can actually put in either in a predefined AWS containers or a custom create container. You can create a container, push your training job inside that container, make it run inside that container, and keep it running till the point you want it. And ultimately it will give you a notification down. Your training job is completed and you can do further. So similarly, there is a Microsoft Azure ML. So they have given this Azure ML. It's similar like of a SageMaker, but I personally worked on a SageMaker, AWS S3, Redshift, EC2 instance, and all that stuff. So that's why I can speak more about them. But Azure, Microsoft is giving Azure ML. And similarly, then we go for a Google. Google has a AutoML. So AutoML they have given right now, and then there is a IBM Watson Analytics. And when I say the Watson Analytics, this is the oldest of all those. So initially they come up with the Watson Analytics and gave it as a service. So if you want actually to have a comparison between these services and which actually specifies your problem statement, then at the time of installing or actually at the time of going for this any service, you need to look into these comparison graphs. And this is the comparison from at the end of 2019, and you can actually have to search for a new comparisons, because in 2019 they were having these services available. For example, in classification, if you go for the machine learning service comparison, classification possible in everyone, regression possible in all, but clustering is not possible in those two, and anomaly detection is only with the Microsoft Azure recommendation engines and ranking and built-in algorithms. And this is what fascinates me about this SageMaker, because I said AWS, Amazon Web Service. This is what is fascinating for me, because I can use a built-in libraries and I can do a custom change in those, because you have it linked with a GitHub, where you can go in a GitHub and take a local pull, change accordingly, and give a pushback and create a custom container of your inbuilt algorithm. Then you don't have to actually rewrite again and again. You just have to import them in your, and then they give these services. MXNet, I told it already depends on your time of problem statement. For example, you sometimes use a PyTorch, sometimes you use a TensorFlow, sometimes Keras, which is again, so the PyTorch is mainly used by the Facebook, and it is predominantly used in academics. So it's very, I mean, I prefer the PyTorch over other the TensorFlow, and because of a support available in PyTorch. Then CabZ and Torch. Okay, so you can see there TensorFlow, Skit, all these libraries, I mean, supported frameworks, and Cognitive and all these toolkit. And then there is a speech and text processing APIs. So if you see here in Amazon, you can get a speech recognition techniques, and sometimes spelling checks is not there. So dictionary you have to actually implement, and auto completion of statements is not again here, and auto completion is not again here. So these things you can actually go through these and check what are the available things, and what are the available things, and what are not the available things.